Now we're going to move on to the example about the Otto engine. This is probably the most important example that I've covered thus far in the entire course. I can tell you that when I entered into my first thermodynamics exam, I actually was really uncomfortable as well with closed systems. So I hope giving you this course and showing these examples of these closed systems and why I would write it the way that I do makes sense to you guys, and you can actually learn how to do closed systems as well. Here we have a closed Otto cycle running with air as an ideal gas and has the following given parameters. So we have a compression ratio of 10.8, P1 of 1.05, T1 of 25 Celsius, V1 of 520 cm3, T4 is 487 Celsius. 1 to 2 and 3 to 4 are isentropic. We neglect the PE and KE, and we have to find pressure, volume, and temperature of all states and sketch the PV diagram qualitatively, the compression work W12, and the heat input Q23. A question like this, where you have to define every single state, is insanely unlikely for an exam, but they could ask for any single one, and I don't want you not knowing how to solve any one of the states, so I will solve all of them for you right now. Now let's start with part A. It is a Otto cycle. This was given, so this obviously is going to be drawn by default. And this is the qualitative diagram. This is just the thing that you saw from the previous lecture. This is always how an Otto's engine is going to look. And sometimes they want you to label what the pressures here are, and maybe what the volumes are. I'm not going to do so, I'm just going to solve all of them, and if you want to add that to the diagram, then do so. So firstly, we can figure out V2, right? This is the easiest one, V1 over CR. These are both given parameters, V1 and CR. So this is going to equal to 520 cm3 divided by 10.8, and that's 48.1 cm3. This is V2, this is one of our numbers. Next up, we go T2 over T1. So T2 and T1 are governed by isentropic, right? It's an isentropic compression. So they are governed by the isentropic exponent. Now, since we're doing temperatures with volumes, we're given the volumes, we have to flip them. So remember, T2 over T1 is V1 over V2. These indices have to be opposite to these ones, don't forget that. This to the power of n minus 1, which is equal to CR to the power of gamma minus 1. N goes to gamma because we have isentropic case, and V1 over V2 by definition is CR. This tells us that T2 itself is equal to T1, which is 298, right? 273 plus 25. Times 10.8, gamma minus 1 is 0.4, we have air, so gamma is 1.4. This gives us 771.9 Kelvin. Next up, we want to get the pressure P2. So of course, we use the same polytropic exponent using the isentropic case, so n equals to gamma equals to 1.4. P2 over P1 to the power of n minus 1 over n equals to V1 over V2 to the power of n minus 1. Couple things. Remember that the v and the mu in your equations can be interchanged here, because you're going to divide both by whatever factor you're supposed to have, r. Right? So it's going to be mu1 over r divided by mu2 over r, for example. So mu and v are interchangeable. And secondly, make sure you memorize these equations, okay? These are very, very important. If they're not given to you in some sort of formulary, make sure you can memorize them. If we move the exponent over to the other side and change n for gamma, we get P2 is equal to P1 times the compression ratio to the power of gamma. And this is going to equal to 1.05, which was given, times 10.8 to the power of 1.4. This gives us 29.4 bars. P2 greater than P1, well, it went through a compressor, so yes, that makes sense. Next up, let's go for T3. T3 divided by T4 is equal to V4 over V3, remember, flip the indices, to the power of gamma minus 1. T3 is equal to T4 times CR to the gamma minus 1. This is going to equal to 760 times 10.8 to the power of 0.4, which is finally equal to 1968.7 Kelvin. Now we have all the temperatures. So given all the temperatures, we can just polytropic exponent every single thing else using the temperature equations. Let's start off with P3. P3 over P2 is going to equal to T3 over T2. Now you can think of this two ways. Either you can think of it as PVRM, BRM. The volumes are the same because it's isochoric. The R is of course the same, and it's a closed system, so the M's are the same. So you can get to this term. Or the fancier route that I like to take is we took the polytropic exponent. So the exponent here was supposed to be n minus 1 over n, as we know. This is an isochoric process, so n goes to infinity. The limit of n going to infinity of n minus 1 over n, this is infinity over infinity, to use L'Hopital from there, gets us a limit of n goes to infinity of the differential of both, which is 1 over 1, which is 1. So this goes to 1 as n goes to infinity. And we still get P3 over P2 equals T3 over T2. Now that tells us that P3 is equal to P2 times T3 over T2, of course. So this is 29.4, solved number from above, times 1968.7, directly copy from above, and T2 is also solved, 771.9. As you see, it's three numbers from above. Try not to get anything wrong, because then this number will be not even close. 74.9 bars is this the largest pressure we expect? Yes. Look at the graph, it's the highest point, right? So this has to be the largest pressure, which it is. Next up, let's go with P4. That's also our last term, right? So what else will we go for? P4 is equal to P1 times T4 over T1. So this is going with the isochoric route. P4 is equal to 1.05 times 760 divided by 298. This gives us 2.7 bars. For the people who want to be a bit more interesting, and you wanted to solve this via the isentropic expansion case, that's of course also doable. T4 is equal to T3 to the power of P4 over P3, power of gamma minus 1 over gamma, right? This is the isentropic case, so we have this. Now, P4 itself, if we rearrange the terms, it's P3 to the T4 over T3. Move the exponent to this side, gamma over gamma minus 1. This is equal to 74.9 times 760 divided by 1968.7 to the power of 1.4 over 0.4. And if you put this in your calculator, you also get 2.7 bars. So they're exactly identical. Now, if we just copy down all the numbers we got here, we can fill it into this little table. P1 was 1.05 bars, 29.4 bars for P2, P3 is 74.9, and finally P4 is 2.7 bars. V was in cm cubed, 520 for these two, and 48.1 for the other two. If this doesn't match, like if these two don't match and these two don't match and you have an Otto cycle, you know you messed up. Lastly, we have temperature. So the first one was given, 298. Then we had 771.9, 1968.7, and finally the last given one was 760 Kelvin. Perfect. Now we go on to doing a power balance once again. So power balance, this time we're trying to get 1, 2. So power balance of 1, 2, 2 gets us, well, this is the general first law. Now let's think about this. Closed system, so this is 0, this is 0. And we have an isentropic case. What does isentropic mean? Adiabatic plus reversible. Adiabatic, that term's also 0, right? Isentropic. So now we end up with dE over dt. dt is equal to W dot 1, 2. Again, we integrate both sides. We get U2 minus U1 equals to, without the dot, W1, 2. And that gets us, of course, W1, 2 is equal to mCV dt. Now, which numbers do we not have here? M and CV. We don't have either. So let's solve both. M is equal to PV equals to MRT. So let's go with P1, V1. Over RT1, subbing in the numbers here, we have 1.05 bars, so 10 to the 5th, times 520 cm cubed, so 10 to the negative 6, right? Because 1 cm is 10 to the negative 2 meters, and then that's cubed, so we do negative 2 times 3, negative 6. Divided by R for air is 287, as we discussed very many times. And finally, T1 was 298. Subbing all these numbers in, we get 6.38 times 10 to the negative 4 kilograms. Perfect. And CV itself, remember, CP divided by CV is equal to gamma. So we can say CV is equal to CP over gamma. Now let's write all of this down. 6.38 times 10 to the negative 4 times CP over gamma. CP is, of course, 1004.5 divided by 1.4. This number is something like 717, I think. Something like this. It might be given to you, it might not be. Just always remember this equation for yourself. This times 771.9 minus 298. This finally gives us 217.1 joules. Remember, this case we have joules, okay? Closed systems, we generally just have a unit of energy, so it's standard joules, and for open systems, we standard have a unit of power. If it was an open system, you'd usually have a dot here and have watts. So make sure you know if you're a closed or an open system and what your final unit should be because of that. And lastly, we had to solve, what was it? Q23, if I'm not mistaken. Yep, Q23. So this, of course, is now a power balance from 2 to 3. M.0, M.0. Well, obviously, because closed system. And 2 to 3 was an isochoric heat expansion. Isochoric means there's no volume change work. Integral of P dV, V1, V2, if they're the same, what does that mean? That's 0. So there's no volume change work, no work, right? Imagine you draw a PV diagram. Actually, we have a PV diagram. What is the area under the curve of this step? That's right, absolutely nothing. So we know that we have no work here. We're left with these two terms. We take the integral and we end up with, let's just simplify it, U3 minus U2 is equal to Q23. Q23 itself is now going to equal to mCV T3 minus T2. All of these numbers we were given above, so equals to 6. Let's just copy this chunk over here. 1968.7 minus 771.9. This is going to end up with 547.9 joules. That's all it really takes. Just don't forget that when I have a closed system, I always, very importantly, need to take my CVDT, okay? Make sure you convert this to the U side and then take CVDT. Yes, hope this really helped. I hope you guys are now comfortable solving with Otto engine. If you are, you are more advanced than I was when I started off with thermodynamics.